carbonyl compound will react with diol in the presence of boron trifluoride and THF. So if you are reacting it with diol, then you probably will need to use 2 equivalents of the diol, and the product of the reaction will give you something that is similar to ketols and acetols. For the purpose of practicality of this reaction, I would rather use a diol and put a cap on the molecule as we did in oxygen nucleophiles with formation of the protecting group. The reason behind that is that through this reaction, we will be able to form a diene, which is very useful for formation of ketones and aldehydes, okay? So we're going to start with a very, very simple carbonyl compound, formaldehyde. So I want to have just the hydrogens attached to the carbonyl carbon. And instead of 2 equivalents of diol, I'm going to bring diol. So let's see what will happen here. Hopefully, guys, you remember from OChem 1 that in hydroboration oxidation reaction, we used borane, BH3, and it was always used with THF because THF will not let the molecule of borane to dimerize, but rather complex with THF and make a better catalyst for the reaction here. So let's take a look at this. My trifluoroborane carrying an empty orbital will easily complex with tetrahydrofuran, which can provide lone pair of electrons to be shared with the empty orbital. And as a result, we're going to form a complex in which oxygen carries positive charge, boron carries a negative charge. Of course, we understand it will be one of the fluorines that will be carrying negative charge, or the negative charge will go back, that electron will go back onto oxygen. So when we are looking at this setting, we understand that boron is becoming more reactive, okay? And in this complex, it will be provided as a monomer to the reaction mixture and not as a dimer, which will pretty much make it unreactive at all. So your oxygen, in this case, is going to easily donate electron density to boron, and we will form the intermediate. Okay. And now it's more reactive. And sulfur can attack oxygen, carbon, carbonyl carbon, bond to oxygen will open up. Okay. Now, I need that complex to leave, the one that has oxygen with boron trifluoride on. So, and my sulfur is carrying a positive charge here. I can perform a quick proton shift. Now we have a good leaving group. Sulfur will be able to attack this carbon. Leaving group will leave. And we will form and we will form, actually over here we have a negative charge. We have a negative charge here, and we will be left with our last intermediate. Proton on. That proton can be removed by your byproduct. Okay, again, understand that boron shows the negative charge on, but either fluorines or hydroxy group will be carrying a negative charge. I'm going to pick up that proton. And form the product. Okay. And hopefully now, guys, you see what was the reason of using formaldehyde as our substrate is because if I formed this product now, I have a really good substrate to form a new aldehyde or a ketone. So I can continue with this reaction. If you go back to synthesis of ketones and aldehydes, you can see that you can proceed with this reaction. And let's just proceed with that. It's not continuation of this mechanism, but if we proceed with this, add Bewley. In the second step, add alkyl halide. And in the third step, react this compound with mercury catalyzed acidic solution. We would form a different aldehyde. But if we wanted a ketone, then after step 2, we would add another equivalent of Bewley, another alkyl halide, and then complete the reaction with removal of the diethion cap. So this is a very good reaction for proceeding, going towards the new compounds. Dithions by themselves are not useful for anything, but for the further synthesis, okay? One more thing, and probably that would be our last reaction, is that dithion can be also reduced all the way to alkane. So let's just put, again, a little roadmap here for you guys. So you would see that if you have a carbonyl compound, and reacted with dithiol, you will form thiine. This time it will be 1,3-dithiene. And then from here, you can proceed. It's a really good synthetic tool. You can proceed by making an aldehyde. Oh, making a ketone, actually. Okay. Or you can proceed by hydrogenating this and making an alkane. Okay. In this case, please keep in mind that if you want to continue with that, the continuation step for here, X will have to be a hydrogen. Because if you started with a ketone, you won't be able to move on to formation of the ketone. If you started with the aldehyde, you could form a ketone. And in both cases, you will be able to make an alkane. Okay? Well, good. So this concludes the reactions of carbonyl compounds and synthesis of carbonyl compounds. So we already put a little chart. I believe we did put a chart for synthesis of both aldehydes and ketones. So let's see if together we can put a chart for all reactions of carbonyl compounds, ketones and aldehydes on one page. So you will have a good reference point for yourself to go through this endless reactions over the weekend. Okay. If you guys have any questions, please ask. And then for the remainder of the time, we're going to try some more synthesis problems together. I really do not want to start chapter 19 yet. I want to give you a peaceful weekend to study only for those 2 chapters, so you're well prepared for the exam. We still have plenty of time to cover everything, so I'm not in a big hurry. Okay. So.
Mrs. O.
Yes.
I just want to double check the sulfur as a nucleophile falls under the cationic reactions, correct?
Yes.
Okay,
Yes.
Thank you.
Okay, so let's move on. Okay. So we already have learned that we're going to break the reactions into anionic and cationic. Ellen, thank you for bringing that up. So let's put those reactions in. First, we're going to look at anionic reactions. And then cationic ones. So your anionic reactions, let's just one more line here. Hopefully that will be sufficient enough. Hydrogen as a nucleophile. But make sure that we know the reaction conditions. You can use either sodium borohydride or lithium aluminum hydride, because these compounds are reactive enough. You can use a mild reducing agent such as sodium borohydride, okay? You really do not have to go after lithium aluminum hydride. Why I'm emphasizing this? Because I saw that the student would say, well, there will be no reaction with lithium aluminum hydride. No, it will be a faster reaction. You will be just wasteful by using more expensive chemicals. So with hydrogen as a nucleophile, the conditions are sodium borohydride or lithium aluminum hydride, followed by the second step. You can use methanol or water or dilute acid. All of this will give you the second protonation step. We're going to have primary alcohols for aldehydes and secondary alcohols for ketones. Okay? Second is the carbonous nucleophile. And so let's remember the reactions that we utilized here. You could use as your carbon nucleophile. Let's put those conditions. Or organometallic lithium, or, and that would be again a special case because only for acetylides you were bound to have sp hybridized carbon as your nucleophilic carbon. For the rest of them, it really doesn't matter. One of them, and second step will be dilute acid processing to form an alcohol. Okay. The outcomes of the reactions, let's put R prime here, will be formation of a secondary alcohol with the aldehydes and formation of, actually, let's put R2 prime because, okay, and formation of a tertiary alcohol with the ketones. Guys, for all of these reactions, please make sure that you understand that your stereospecificity matters. Okay, so let's just identify the type of alcohol. You will be forming secondary here and tertiary here. Stereospecificity will matter. So if you have no other chiral centers, you have a linear molecule, you will be forming racemic mixture. If you have other chiral center on the linear molecule that is not affected by the reaction, you're going to have a one-to-one mixture of diastereomers. If you have cyclic compound, you will have major and minor products. So please do pay attention to stereospecificity on your exam. With carbon as a nucleophile, we also had one more reaction. So let me bring that line down. your Wittig reaction as a special case. This is hydrogen as a nucleophile. Okay, and for Wittig reaction, we will form wait, let me put a little bit more clarity in here. Chlorine or bromine doesn't matter, but this carbon must be secondary or primary. Okay. And of course, here you will have your X, and X will be either hydrogen or the R prime group. So carbon nucleophiles, hydrogen nucleophile outcomes are given. So let's take a look at the outcomes of the reaction with oxygen and nitrogen and sulfur. And hopefully we will be able to fit the whole thing on one page. We'll just be optimistic about it. Okay. Oxygen nucleophile, nitrogen nucleophile, and sulfur nucleophile. Okay, with oxygen nucleophile, we're going to form ketal or aldehyde or acetal. Special case here, if your oxygen source is a diol, then in that case you will be forming a protecting group. Okay. With nitrogen nucleophile, we're going to break it into categories. So let's put a box for imines and enamines. Let's put nitrogen sources, NH3, NH2OH, NH2, NH2, and NH R. Okay, NH2R. So here are our nitrogen sources. Let's see what will happen. The reaction conditions are again the same. Okay. Let's put a little extension for the enamine hydrogen reaction. Step 2 with KOH. Here are X's. So we're going to extend it a bit. And finally, when we have a primary amine, geometry should be trans for larger groups. For enamines, your source of nitrogen is a secondary amine. And you will be forming an enamine. Okay, more substituted alkene. Okay, so let's separate our oxygen nucleophile. Nitrogen nucleophiles, and we have very little space for sulfur as a nucleophile, so let's just try to squeeze that in, and hopefully we will be able to fit this portion, and if not, you'll find a place for it and put it in. So let's see. The reaction conditions. Oops. BF3, THF. Okay, you put this on and you can reduce it. And form an alkane. Okay, and for compounds where X is hydrogen, let me continue with that. Special case, when X is hydrogen, then you can run the reaction all the way to formation of a ketone. Let me zoom in so you will be able to see it.